then you get Kirchhoff's. Kirchhoff's rule is simply a special case of Faraday's law. And Faraday's law always holds. So Kirchhoff is for the birds, and Faraday is not. Suppose you go from D to A and back to D. Well, we know that Vd minus Va, if we go through this, if we go this way through R2, we know that Vd minus Va is plus 0.9 volts. Now we are at A, and we go through the left side back to D. So we now have Va minus Vd. That, of course, is now plus 0.1 volts. Because remember, if Vd minus Va is minus 0.1, then Va minus Vd is plus. And so we add them up, and we find that Vd minus Vd is plus 1 volt. Kirchhoff said, has to be 0, because I'm back at the same potential where I was before. Faraday says, I'm sorry, you can't do that. That 1 volt is exactly that EMF of 1 volt. That is the closed loop integral of E dot dl around that loop. It's no longer 0. And therefore, whenever you define potential difference, if you do that in the way of the integral of E dot dl, keep in mind that with non-conservative fields, it depends on the path. And that is very non-intuitive. And I'm going to demonstrate this now to you. I have a circuit which is exactly what you have here. I have 900 ohms in a conducting copper wire here, and I have 100 ohms here, and here is the solenoid. And we can switch the current on in the solenoid, we get a blast of magnetic field coming up, and the system is going to react by driving a current in the direction that you see there. And I'd like to be even a little bit more quantitative so that you get a little bit more for your money. The magnetic field takes a little bit of time to reach the maximum value. In this course, we will be able to calculate the time that it takes for the magnetic field to build up. We didn't get to that yet, so forget that part. It's not so important. I just want you to appreciate the fact that the magnetic field, as a function of time, will come up like this and will then reach a maximum. It's no longer changing. It's constant. It's a maximum value. It's very high. It's 700-800 Gauss or so for this unit. We are not interested in the magnetic field. We are interested in the change of the magnetic field. So the change of the magnetic field, dB dt, is going to be something like this. That's the derivative of this curve. And that is proportional with the induced EMF, and that's proportional with the current through Ohm's law. So if we now plot the voltage as a function of, let me do that here, the voltage as a function of time, then that voltmeter on the right side, I call that V2, will do this. This is V2, which is I times R2. At the maximum value, if those values were correct, it would be 0.9 volts. And V1 will go like this. V1 equals minus I times R1. That gives me the minus 0.1 volts. So the question now is, what is the largest value of the BDT that we can expect? We also have to know the surface area of the solenoid, so we can convert it to a flux change. Well, the change in magnetic field is roughly at the fastest here is about 100 Gauss in 1 millisecond. Very roughly. So that would mean a field change dB dt, that's the maximum value possible only in the beginning, of about 10 Tesla per second. And the surface area, which is that inner circle there through which the flux is changing, the fact that my surface has to be attached to that loop doesn't change the magnetic flux. The magnetic flux is only determined, of course, by that inner portion. And so if the inner portion has an area of, say, 10 square centimeters, which is 10 to the minus 2 square meters, then the phi dt will be approximately 10 times 10 to the minus 2, so that's about 0.1. And that's volts. That's EMF. I don't care about the direction because I know Lenz's law. So you're going to see an experiment which is almost identical to what I have there, except all values are down by a factor of 10. But that's all. And you're going to see that demonstration there. And a few years ago, when I first did this experiment in 26100, there were several of my colleagues, professors of both the physics department and the E department, in my audience. And some did not believe what they saw. In fact, it was so bad that after my lecture, they came to me and some accused me for having cheated on the demonstration. This tells you something about them. Imagine professors in physics and professors in electrical engineering department who did not believe what they were seeing. That tells you how non-intuitive this is. The simple fact that we had one voltmeter connected to point D and A, and another voltmeter connected to the same point, they were unwilling to accept that the two voltmeters read a totally different value. They were not used to non-conservative fields. Their brains couldn't handle it. But that's the way it is. And I'm going to show this to you now. You're going to see it there. And when you see this demonstration, it will be probably the only time in your life that you will ever see this. And I want you to remember this. You're going to see something that is very strange, and I want you to tell your grandchildren about it. That you have actually seen it with your own eyes. You're going to see it there. On the left side, you're going to see V1, and on the right side, you're going to see V2. The vertical scale is such that very roughly, from here to here is about 0.1 volts. And a horizontal unit is about 5 milliseconds. And the whole voltage pulse lasts about 10 milliseconds, because from here to here is about 10 milliseconds. And the value that you expect for V2 will be 9 times higher than V1, and the polarities will be reversed. If you're ready for this big moment in your life, 3, 2, 1, 0. Look on the left, there's V1. Notice, it's negative. Look on the right, there's V2. It's about 9 times larger than V1. Don't pay any attention to this wiggle that has to do with the voltage that we apply, which is not exactly flat. And notice that the whole pulse goes from here to here, lasts about 10 milliseconds. The moment that the magnetic field reaches a maximum and remains constant, there is no longer any induced current. Think about this, give this some thought. This is not easy, and have a good weekend.